Jean-Robert Argand lived an extraordinary life, though he was a humble man. Born in Switzerland in 1768, he was a true child of the Enlightenment. From a young age, he displayed a keen intellect and an unquenchable thirst for knowledge. Despite not having the privilege of formal higher education, Argand's passion for learning burned brightly. He was particularly drawn to the world of mathematics, a subject he pursued with relentless dedication through self-study. Argand's early life was marked by both personal and intellectual challenges. Yet, he persevered, his love for mathematics serving as a constant source of inspiration. He devoured every book and treatise he could lay his hands on. His dedication bore fruit as he steadily mastered complex mathematical concepts. Little did he know that he would one day make a groundbreaking contribution to this field. His journey was a testament to the power of self-belief and the pursuit of one's passions. Argand's early explorations in mathematics laid the groundwork for his later achievements. He delved into the intricacies of algebra and geometry, his mind constantly seeking patterns and connections. It was during these formative years that he first encountered the enigmatic concept of imaginary numbers. These numbers, with their perplexing properties, captivated his imagination and set him on a path that would change the course of mathematical history. Argand's early life was a testament to the power of curiosity and the importance of self-education. It was during these years spent poring over books and wrestling with complex ideas that he developed the intellectual tools and the unwavering determination that would shape his future endeavors. His story is an inspiration to us all, reminding us that greatness can emerge from the most humble beginnings. In 1806, seeking a wider audience for his intellectual pursuits, Argand moved to Paris, the vibrant epicenter of European intellectual life. The city was a melting pot of ideas, where scholars, artists, and thinkers from all over the continent converged. Amidst this stimulating environment, Argand found himself drawn to the bustling bookstores that lined the banks of the Seine. He secured a position as a bookseller, a role that perfectly complemented his love for knowledge. Surrounded by books on every conceivable subject, Argand immersed himself in the world of ideas. He engaged in lively discussions with customers and fellow booksellers, debating the latest scientific discoveries and philosophical treatises. His days were filled with the written word, and his mind became a fertile ground for new ideas to take root. Despite the demands of his work, Argand never abandoned his passion for mathematics. In the quiet hours after closing time, he would retreat to a small room above the bookstore, transforming it into his personal sanctuary of mathematical exploration. Here, surrounded by stacks of books and illuminated by the warm glow of an oil lamp, Argand delved into the mysteries of complex numbers. It was during these late-night sessions, fueled by endless cups of coffee and an unyielding determination, that Argand made his groundbreaking discovery. Inspired by the geometric representation of negative numbers on a number line, he envisioned a way to visualize imaginary numbers as well. This epiphany, born from countless hours of contemplation and fueled by his passion for mathematics, would change the way we understand numbers forever. Argand's most significant contribution to mathematics was the development of the Argand diagram. This elegantly simple yet profoundly powerful tool provided a visual representation of complex numbers, unlocking a deeper understanding of their properties and relationships. Prior to Argand's innovation, complex numbers, with their so-called imaginary component, were often viewed with skepticism and confusion. The Argand diagram brought clarity to the chaos. It consists of two perpendicular axes, much like the familiar Cartesian coordinate system. The horizontal axis represents the real number line, while the vertical axis represents the imaginary number line. Any complex number with its real and imaginary components could now be plotted as a point on this two-dimensional plane. This visual representation revolutionized the way mathematicians perceived complex numbers. No longer were they abstract entities confined to the realm of algebraic equations. The Argand diagram allowed mathematicians to see complex numbers, to grasp their geometric relationships, and to manipulate them with a newfound clarity. The impact of Argand's diagram was immediate and profound. It provided a bridge between the worlds of algebra and geometry, demonstrating that complex numbers were not merely mathematical curiosities, but rather powerful tools with far-reaching applications. The Argand diagram became an indispensable tool for mathematicians, physicists, and engineers, paving the way for advancements in fields as diverse as fluid dynamics, electrical engineering, and quantum mechanics. Building upon the foundation of the Argand diagram, Argand introduced two crucial concepts, the modulus and the argument of a complex number. These concepts provided a new way to represent and understand complex numbers, further enriching their geometric interpretation. The modulus, denoted by the absolute value of a complex number, represents the distance of the point representing the complex number from the origin on the Argand diagram. The argument, on the other hand, captures the direction of the complex number. It is the angle measured counterclockwise between the positive real axis and the line connecting the origin to the point representing the complex number. Together, the modulus and argument provide a complete polar representation of a complex number, complementing its Cartesian representation. This polar representation, made possible by Argand's insights, opened up new avenues for understanding and manipulating complex numbers. It revealed a hidden elegance in their structure, demonstrating that complex numbers could be viewed as vectors on the Argand plane, characterized by their length, modulus, and direction, argument. The concepts of modulus and argument proved to be invaluable tools in various mathematical operations involving complex numbers. They simplified calculations, provided geometric insights, and led to a deeper understanding of the behavior of complex numbers. These concepts, born from Argand's geometric intuition, continue to be fundamental in fields like electrical engineering, where they are used to analyze alternating currents, and in quantum mechanics, where they play a crucial role in describing the state of quantum systems.